So, we may actually consider it in a slightly broader sense. In place of mu is equal to 0 and mu is equal to 1, if we substitute say some values mu naught and mu 1, and then let us see the effect of this. So, now let me generalize this problem. X 1 x 2 x n follows normal mu 1, and we are testing the hypothesis whether mu is equal to mu naught against h 1 mu is equal to mu 1, where let me take mu naught to be less than mu 1. Now, let us write down the density ratio, that is f 1 x divided by f naught x. So, it is 1 by root 2 pi to the power n e to the power minus 1 by 2 sigma x I minus mu naught square, sorry, this one will be mu 1 square divided by 1 by root 2 pi to the power n e to the power minus 1 by 2 sigma x I minus mu naught square. Now, you can see that these terms cancel out, e to the power minus 1 by 2. If you expand this, you get sigma x I square minus twice mu 1 sigma x I. So, after simplification, this term becomes e to the power n mu 1 square minus mu naught square with a minus sign e to the power mu 1 minus mu naught sigma x I. Remaining terms get cancelled out here. So, now if we look at the most powerful test, this is reject h naught if f 1 x by f naught x is greater than or equal to k. So, if we utilize this here, given mu 1 and mu naught whatever be the values, this is some constant here. So, this region is reducing to e to the power mu 1 minus mu naught into sigma x I greater than or equal to say some k 1. So, if mu 1 is greater than mu naught, then this region is equivalent to x bar greater than or equal to some k 2. Therefore, the test is to once again reject h naught for larger values of x bar. So, if you compare with the previous situation where I had taken mu naught to be 0 and mu 1 is equal to 1, then we were rejecting for larger value of x bar. So, as I mentioned here that the only deciding factor is the value of x bar, and but we wanted to know the scale of x bar, that on what scale we will consider x bar to be large or what should be the small value, that is decided by the probability of the type 1 error. So, in the same way here you are seeing that if mu naught is less than mu 1, the region is actually same, but how much it is same, that will be dependent upon the probability of type 1 error. So, if we write here probability of x bar greater than or equal to k 2 when mu is equal to mu naught, this is equal to alpha, then we observe the distribution here. So, the distribution of x bar here is normal mu 1 by n. So, under h naught x bar follows normal mu naught 1 by n. So, we can do the calculations here by simplification, x bar minus mu naught into root n, that will follow normal 0 1 distribution. So, under h naught this statement can be written to be equivalent to z greater than or equal to some k is equal to alpha. In place of k, let me write here k star, where z is defined to be root n x bar minus mu naught. So, this point k star becomes the upper 100 alpha percent point of the standard normal distribution. This is the point k star. This probability is alpha. Therefore, this k star is actually z alpha point here. So, as a practical example, if we substitute different values here, say mu is equal to -1, then the rejection region is changing root n x bar plus 1 greater than or equal to z alpha. We have seen the example earlier that if I am putting say alpha is equal to 0.05, then z alpha is equal to 1.645. So, the test will become in that case root n x bar minus mu naught greater than or equal to 1.645. This is the rejection region. So, if I say take mu naught is equal to say -1, then this will become root n x bar plus 1 greater than or equal to 1.645. So, if we compare with the previous example where mu was 0, then it was root n x bar greater than or equal to 1.645. So, the magnitude of x bar which will be considered to be large depends upon the probability of the type 1 error, and that means what is the value of the probability distribution point when mu is equal to mu naught. A similar behavior is observed. Suppose we consider testing for the variance in normal distribution case. Let me take the case of say x 1, x 2, x n. For convenience, let me take the mean to be 0 and variance to be sigma square, and we are interested to make a test of hypothesis about say sigma square. Now, once again let us write down the density function here f x sigma square. So, we need to write for the joint distribution of x 1, x 2, x n here. So, that is 1 by root 2 pi sigma to the power n e to the power minus 1 by 2 sigma square sigma x I square. Since I have taken the mean of the normal distribution to be 0. So, the joint distribution of x 1, x 2, x n turns out to be this one. So, we write down this value corresponding to the null and the alternative hypothesis. So, when sigma square is equal to sigma naught square, then this is becoming 1 by root 2 pi sigma naught to the power n e to the power minus 1 by 2 sigma naught square sigma x I square, and f 1 x in a similar way will become 1 by root 2 pi sigma 1 to the power n e to the power minus 1 by 2 sigma 1 square sigma x I square. So, if you consider the ratio f 1 x by f naught x, that is equal to, so now this will become equal to sigma naught by sigma 1 to the power n e to the power 1 by twice sigma naught square minus 1 by 2 sigma 1 square sigma x I square. So, by Neyman-Pearson lemma, the most powerful test of H naught versus H 1 is reject H naught if f 1 x by f naught x is greater than or equal to k. Once again we notice here that this distribution of x is continuous distribution. So, the distribution of the variables involved here, for example, here sigma x I square is involved, that is also continuous distribution. So, here without loss of generality we can write greater than or equal to, because the probability of the statement being equal to k, that is f 1 by f naught equal to k, that probability will be 0. So, this equality can be included here. So, now if we look at the ratio here, this is greater than or equal to k, then this will reduce to, because sigma naught and sigma 1 are the known constants. So, this condition is gone, and if we take the logarithm, then we get it as this condition is equivalent to one by 2 1 by sigma naught square minus 1 by sigma 1 square sigma x I square greater than or equal to some k 1. Now, once again the relative position of sigma naught square and sigma 1 square is playing a role here. So, if suppose I take sigma naught square to be less than sigma 1 square, then this will be equivalent to 1 by sigma naught square greater than 1 by sigma 1 square. Therefore, the region will be equivalent to sigma x I square greater than or equal to say k 2, where this k 2 has to be chosen in such a way that sigma x I square greater than or equal to k 2 has a probability equal to alpha when sigma square is equal to sigma naught square. So, the condition becomes sigma x I square greater than or equal to k 2 when sigma square is equal to sigma naught square is equal to alpha. So, in order to find out the value of k 2, we need to look at the distribution of sigma x I square when sigma square is equal to sigma naught square. So, we look at our statement here x 1, x 2, x n they followed normal 0 sigma square, and therefore, if we consider sigma x I square by sigma square, that will follow chi square distribution on n degrees of freedom, because we are considering this to be random sample. So, these are independent and identically distributed random variables. So, under H naught, let me call it W, that is sigma x I square by sigma naught square, that follows chi square distribution on n degrees of freedom. So, we can write down this statement as W greater than or equal to some k star is equal to alpha. So, since W is following chi square n distribution, the point k star becomes upper 100 alpha percent point. This point is k star and this is alpha. So, this point is nothing but chi square n alpha. That means, the test is reject H naught if sigma x I square by sigma naught square is greater than or equal to chi square n alpha. Let us interpret this test here. We wanted to test whether the variance of a normal distribution is less or more, because sigma naught square we took to be less than sigma 1 square. Now, when mean is taken to be 0, sigma x I square by n is a estimator. We have actually calculated the maximum likelihood estimator. So, that is an estimator for sigma square. So, as a layman you will base your decision on the value of sigma x I square by n. That means, for a smaller value of sigma x I square by n we will tend to accept H naught, and for a larger value of this we will tend to accept H 1, that is rejecting H naught. So, now how much value of sigma x I square by n should be considered small or large, that is decided by the probability of the type 1 error. So, if the probability of the type 1 error is alpha, the relative position of sigma x I square is decided by chi square n alpha, and of course, the value sigma naught square also plays a role, because if sigma naught square is much smaller compared to sigma 1 square, then that value will play a role. So, the test here you can see that relative position is dependent upon the value of the parameter in the null hypothesis, and for the power function it is reverse. We are making use of the alternative hypothesis value, that is the power will increase or decrease according to the value of the parameter in the alternative hypothesis here. Now, we have seen here application of the Neyman Pearson lemma to some continuous distribution, especially normal distribution. we have seen the application to some discrete distribution such as a binomial distribution. So, this is a very general result, because I can consider any distribution, and if we have a simple versus simple hypothesis. So, in fact, it is not even necessary that we have a same form of the distribution as we have seen in the first example, where under the null hypothesis we had a uniform distribution, and under the alternative hypothesis we had another distribution which was having a density 2x. So, in general we are able to test whether we have this probability distribution which is completely specified, or another one which is again completely specified by making use of the Neyman Pearson fundamental lemma. Another important point that you may notice here is that in most of the situations the test function is coming in terms of the statistic which is actually a sufficient statistic. You can also say that it is coming in the terms of the maximum likelihood estimator, as we have seen in the examples of the normal distribution, where for mu you got in terms of x bar, and for sigma square we, when we are doing the test, then it is coming in terms of sigma x I square. Naturally, we can check for certain other distributions also, such as say let x 1, x 2, x n this follow an exponential distribution with some parameter say lambda. Before I discuss this example, let me take the other case also, where sigma naught square may be greater than sigma 1 square. Then let us see how we are distinguishing. If sigma naught square was greater than sigma 1 square, then 1 by sigma naught square is becoming less than 1 by sigma 1 square. Now, if you see here, this value will become negative. Therefore, if I divide by that value, the region is becoming reverse. So, we are getting the region as, then the rejection region is sigma x I square is less than or equal to k, say k 1, or let me put it in another way in place of. So, once again we will have probability of sigma x I square by sigma naught square less than or equal to some k star is equal to alpha. So, here it is turning out to be the left hand point. We are saying this value is alpha, that means this upper value is 1 minus alpha. So, this k star in this case becomes chi square 1 minus alpha n point. That means, the test is to reject h naught if sigma x I square by sigma naught square is less than or equal to chi square 1 minus alpha n. So, you can see here that the region has got reversed. Why? Because now the null hypothesis supports a larger value of sigma square, that is sigma naught square I have taken to be bigger than sigma 1 square. So, a smaller value of sigma x I square will be in favor of the alternative hypothesis, which is against the previous case, where a higher value was supporting the alternative hypothesis. And once again, that on the relative scale, that how much value of sigma x I square will be considered to be larger or smaller, that is determined by the probability of the type 1 error and the value of the parameter in the null hypothesis here. Now, let me consider the example which I mentioned earlier, that is of a exponential distribution, and we may like to test say lambda is equal to say 1 against say lambda is equal to 2. Now, the question is that when we are discussing distributions which are different than the normal distribution etcetera, we may get a statistic where the distribution of the statistic which is appearing in the test function may not be simple. Then we may have to use certain transformations and get the distribution of that. so that one may make use of the tables of the standard distributions to find out the exact test of the hypothesis. So, in this particular case, for example, let us write down the joint distribution. So, f 1 x by f naught x. So, here the joint distribution f x lambda, that becomes lambda to the power n e to the power minus lambda sigma x I, when all the x i's are positive, it is 0 elsewhere. So, f 1 will be correspond to the value of lambda is equal to 2, then this becomes 2 to the power n e to the power minus twice sigma x I divided by, when I put f naught, that is corresponding to lambda is equal to 1, I will get e to the power minus sigma x I. So, we are saying the test is reject h naught if this is greater than k. Once again, without loss of generality, we may include equality here or we may delete equality, because the distribution of x i's are continuous, therefore, the distribution of sigma x I will also be continuous. In fact, we know the distribution of sigma x I here. Firstly, let us simplify this. So, this region is equivalent to, if we take this in the numerator, it is reducing to sigma x I greater than or equal to some k 1, because this coefficient we can remove, and when we take logarithm, this is reducing to sigma x I less than or equal to some k 2. Now, we have to find out the value of k 2 such that the probability of type 1 error, that is sigma x I less than or equal to k 2 is equal to alpha. So, we make use of the distribution theory here, as I was mentioning. Sigma x I will follow gamma distribution with parameters n and lambda by the additive property of the exponential distribution. The sum of independent exponential variables is a gamma variable. So, under h naught, sigma x I will follow gamma distribution on n and 1 degree of freedom. Now, what is this distribution? If we write down, let me denote it by say y, then the density of y is 1 by gamma n e to the power minus y, y to the power n minus 1. So, if we consider say 2 y is equal to say w, then the distribution of w is equal to 1 by 2 to the power n gamma n e to the power minus w by 2 w to the power n minus 1 for w greater than 0, which is nothing but probability density function of a chi square distribution on 2 n degrees of freedom. So, now under h naught, we can write this as probability of w less than or equal to some k star, that is equal to alpha. So, this w is having a chi square distribution on 2 n degrees of freedom. So, this point that you are having here, this is such that this probability is equal to alpha and this probability is 1 minus alpha. So, k star naturally turns out to be chi square 2 n 1 minus alpha. So, the test function then becomes reject h naught if twice sigma x I is less than or equal to chi square 2 n 1 minus alpha. Let us again analyze this statement in a practical sense. Here lambda is the rate of the Poisson process. So, basically the mean was 1 by lambda. So, you want to test whether the mean is less or more. So, in fact, the alternative hypothesis is having a higher value, because mean is one reciprocal of that. So, this is actually rate. So, rate is less or more. Now, for the rate, for the average, the variable, or you can say the statistic, you would have been x bar, which is of course proportional to summation of the values here. So, we may even write it in this particular form. This is actually equal to twice n x bar. So, a natural thing would be to go in favor of the null hypothesis if x bar is smaller, because if rate is larger, if rate is smaller, this is corresponding to the mean to be smaller. So, the mean is represented, or you can say estimated by the sample mean. So, for the smaller value of the sample mean, we will tend to favor h naught, whereas for the, I am sorry, I just made the reverse statement. Here the null hypothesis is corresponding to lambda is equal to 1, against the alternative hypothesis lambda is equal to 2. So, if we are considering say mean, then 1 by lambda is 1 and 1 by lambda is equal to half here. That means, under the null hypothesis the mean is smaller, sorry, mean is larger, and in the alternative hypothesis the mean is smaller. That means, when we are using the sample mean as an estimate of that, for the smaller value of the sample mean, we will tend to favor the alternative hypothesis, and for a larger value we will tend to favor the null hypothesis. And the relative significance of how much is larger or how much is bigger is dependent upon the probability of the type 1 error, as well as the value of lambda is equal to 1 and lambda is equal to 1 has been utilized here. On the other hand, if we had say h naught lambda is equal to 1 against say lambda is equal to half, suppose just I make the change here, then what will happen? In the case of the null hypothesis, you will have the same value, whereas in the for the alternative hypothesis this will become half, and this will become e to the power minus sigma x I by 2. So, in that case, in the numerator we will get e to the power sigma x I by 2 with a positive sign, and then the test function will become sigma x I is greater than or equal to something rather than less than something. So, when we analyze this, we get here that test would be to reject for larger value of x bar, which is natural, because when I say lambda is equal to half, that means I am saying 1 by lambda is equal to 2, which is bigger than 1 by lambda is equal to 1 here. So, you can also see that in the Neyman-Pearson lemma, the tests which we are obtaining it by using the theory of most powerful test, they are conforming to a layman's approach, or you can say a likelihood approach for testing the hypothesis. In the next lecture, I will be discussing in the more detail how to find out the tests for the composite hypothesis.